Perspective on.
Thank you, Bill. Thanks to all the organizers. It's been a great week, and I'm really honored to give a talk on some of the recent work we've done on distributed computing, and to give you a preview of the main results. These are quantum distributive algorithms to tackle certain challenging graph problems, and they're in a framework where the information is distributed in the first place. So you have to take a distributed view. And in our first paper that came out last year, we had found asymptotic quantum algorithms with asymptotic improvement in the number of communication rounds over the current best known classical algorithms in a certain model that I'll define. For the Steiner Tree problem and the directed minimum spanning tree problem. We built on prior results, particularly building a routing table that had not been needed in previous algorithms. But one of our main results also is to have done a detailed analysis of the complexity of the main algorithm steps, keeping track of constants and log factors, and recognize that so the non-asymptotic complexity, so we have a provable asymptotic improvement over the current best algorithm, but the non-asymptotic complexity results, to my great disappointment, means that these are not applicable to application scale problems yet. And in the second paper, we generalized these results to a much larger class of problems. And I'll go through this and then have a bunch of open questions in this domain near the end. So let's get started. So I'm going to start with some background. So we're looking at algorithms on distributed data. So we have a network of processors that can communicate. We're going to model these as a graph where nodes are processors. We're just talking about classical for the moment. It could be really any information that's at each of those nodes, but we're going to look at graph problems where, for example, the information may be your list of neighbors and maybe the weights of those edges. No one has a global point of view. And so the goal is to answer some questions about that distributed information through communication and computation among the processors. So there are a number of models you can use, but we're going to be looking at bandwidth limited models. So I'll introduce two classical models. So assume you have a graph with a certain number of vertices, edges, and weights on the edges. And the CONGEST model basically limits the amount of bandwidth you have to communicate it each time. So communication happens in rounds. And we're going to assume unlimited computational capability at the nodes, also a limited memory, but the communication is limited by message size. And we're going to assume that each neighbor can send order of log n bits each round. The log n is because tag for one of those nodes. If you have n nodes, an ID tag for that would be log n. And so you can think of this as sending a constant number of ID tags for nodes in the graph at each round. In this case, in the CONGEST model, we're going to be trying to learn something about the communication graph itself. So before I go on to the next one, any questions on this model? So in the CONGEST-CLIQUE model, we're going to separate the graph that we're going to be trying to learn something about from the communication graph. So all of the nodes can communicate with each other, but they all have information about a different graph. It may be a faster communication graph that you're trying to understand, but where it's the nodes are faster, but I mean the communication between nodes is faster, but it's not everybody's connected. You can think of various scenarios. So, and the initial conditions, each node knows its own ID and the IDs of its neighbors, and it may know weights for that edge on the graph we're trying to learn something about. And then there are various problems you can ask, and I'm going to restrict to graph problems, but we could have other information which broadens the class of problems you might want to consider here.
Or in the underlying graph or the G?
This will be in the graph we're trying to learn something about.
Okay.
So because it's, maybe I should have said this, the clique means everybody can communicate to everybody. So once you have that, you don't really need to say neighbor in the context of the communication graph, because everybody can talk to everybody. And so neighbor, yeah, but that's really helpful to get sorted out at this point. So neighbor here all mean not in the way we're going to communicate for the algorithm, but rather the graph we're trying to learn something about. Yeah.
Aim to minimize the number of rounds to do what?
Various things like find a spanning tree, minimum directed spanning tree, find Steiner tree. I'll give a bunch of examples.
In the minimum number of rounds.
Yeah, so trying to minimize the number of rounds. Yep. Yep. Yeah, other questions? Okay, so a big question here is what problems can benefit from a distributed quantum approach, where instead of just sending bits, we can send qubits, and we can do quantum computation at each node. So the quantum models are the same as before, with the same bandwidth limitations, except that it's qubits. So you can send order log n qubits as opposed to just bits, and you can do unlimited quantum computation at each node. And so these are the two models that we'll look at. There were some prior results in the CONGEST model, so that first one where the communication graph is the same as the one you're trying to learn about. And basically the results were quite negative, that quantum communication does not provide an improvement for a variety of graph problems. And the intuition from our point of view is that you have a significant bottleneck in the communicating between distant parts of the network, and qubits just don't help with that. One thing I want to clarify is that we are not assuming entanglement or anything ahead of time. We're just assuming separate nodes, et cetera, et cetera. You could define a different model where you've set up some entanglement ahead of time, and that could be interesting, but that's not what we're doing here. However, these negative results don't carry over to the CONGEST-CLIQUE model, and there were some positive results prior to us from Legal and co-authors on faster triangle detection in a graph and faster all pairs shortest paths in a graph. And note that these were on Elkin's list of problems that do not admit speedups in the CONGEST case. And so we found particularly the all pairs shortest path inspiring, and wanted to look at for what other problems we can exhibit improvements due to in the quantum CONGEST-CLIQUE model versus the classical. So we have a bunch of new algorithms that build on the older ones, and in particular, the first paper had a new algorithm for approximately optimal Steiner tree problems and directed minimum spanning tree problems, and our more recent paper extends that to survivable network problems, and I'll define these problems in a moment. And these are in asymptotically fewer rounds than required for any known classical algorithm. It's a small polynomial speedup, or not, maybe I shouldn't say speedup, it's a a small improvement in the number of rounds, but it's provable against the best known classical approaches. People neither in the classical case or in the quantum case had done an exact complexity analysis, and so we're going to do that as well. So in a directed minimum spanning tree, given a root node in a directed weighted graph, we want to find a directed spanning tree from the root node so that you can get to all of the other nodes in the graph. And you want the weight to be, you're trying to minimize the weight, okay? We're going to make great use of that fast all pairs shortest path, but we're going to add routing tables which were not previously there. And this is done via triangle finding and a distributed Grover search to obtain faster algorithms. And I'll go through briefly what those are in a little bit. And in Steiner Tree problem, you have a set of terminal nodes, and you want to find a minimum weight tree in the graph that contains those Steiner nodes. And our approximate Steiner tree problem is one whose total weights are no more than r times the weight of the optimal tree. And so we're able to find a good approximation with good probability into the 1/4 rounds of communication, that should say. Where L is the number of terminal leaf nodes in the Steiner tree. And then the survivable network design problem is a very broad class of problems, and basically you're given for any node V, it has a connectivity requirement RV. And the problem is to find the minimum weight subgraph where for any pair of nodes, V and W, there are at least min of RV, RW, so the two connectivity requirements for those two nodes, disjoint paths between them. And it's really remarkably general. So if you take RV to be 1 for all V, that's the minimum spanning tree problem. If you take RV to be 2 for all V, that's a traveling salesman problem. If you take RV to be 1 for the terminal node, for the Steiner nodes, and RV to be 0 otherwise, that's a Steiner tree problem. It also encompasses the shortest ST paths and the K-connected sub network problem that are discussed often for robust networks. And we're able to show that quantum versions require asymptotically fewer rounds of communication, again, going from order n 1/4 plus some log factors versus order n to the 1/3. The approximation ratio varies with problems, but it's generally less than 2. And we have more specific numbers in certain cases. Just to step through this, let each node V have a connectivity requirement RV. We want to find the minimum weight subgraph where any pair of nodes V and W, there's at least min RV, RW disjoint paths connecting them. So just as an example, if we have RV equals 2 on the pink nodes and RV equals 1 on the black nodes, well, we can see very quickly that there's one path between the pink nodes this way and another path this way, and those are totally disjoint, which is great. And then for our RV equals 1, we just need to make sure that there's a path between all of the black nodes, which is fairly easy to see. So that's the survivable network design problem. The reason this is interesting is, for example, if K edges are deleted, any node with connectivity numbers greater than K remain connected. And so that's why it's called survivable network. So yeah, before I go into the algorithmic recipe, any questions on the survivable network problems? So we're going to make use of previous techniques such as distributed Grover search, triangle finding, distance products, and shortest paths and routing tables. Distributive Grover subroutine is, say you're given a set X of inputs and a node U, which we'll call the leader, and suppose that U can evaluate a certain function G in R rounds. Then there exists a quantum distributed algorithm such that you can output a marked element X in R times root X rounds. I just realized I'm using R for two different things I apologize. So R's rounds here, whereas it's the R's with sub indices are the connectivity requirements. So yeah, so this uses the same ideas as a centralized Grover search, it's the same square root improvement. And the intuition is that a node wants to inquire about something related to some subset of other nodes. And instead of inquiring one node at a time, it can do so in superposition and get the information somewhat more quickly. And then we can make use of distributed Grover search to find triangles. Why do we want to find triangles? We'll see in a bit that is a step along the way to get all pairs shortest paths. And so triangles live in V cross V cross V. And what we're going to do is partition that space into n subsets, one subset per each node, so the node can do a search on that partition. And there are different ways you can partition, and it turns out to be good if we partition the first two into if we partition this into a bunch of different subsets indexed by V1, V2, V3, where the size of V1 and V2 is n to the 1/4 and V3 is n to the 1/2. As you can see, if you multiply those together, you'll get n subsets. So we can give one of those to each node. And if we look at what each of those nodes has to do, well, it's going to have, for V1 and V2, it contains n to the 3/4 nodes, and V3 contains n to the 1/2 nodes. And so we're going to make use of the fast routing. And the bottleneck comes through searching elements of V3. So distributed Grover search, we can do this in n over 1/4 rounds instead of n over 1/2. And then we're going to use that in the context of distance products. So a distance product is familiar to some folks, but it's for some reason not as common to see. So a distance product between two n by n matrices A and B, and it's also sometimes referred to as the min plus or tropical product, is just defined by the min of the appropriate indices. So each of the entries ij is the min of aik, the entry aik plus bkj over all the different possible k's. And if W happens to be the adjacency matrix of a graph, then the ijth entry of the distance product of W with itself gives the shortest hop path, two-hop path from node I to node J. And then W to the n will contain the shortest n-hop distances. So it will tell us all the shortest path distances in an n node graph. So that's a distance product, and we're going to use subroutine fine triangle, negative triangle triangles on an n node integer weighted graph, and if we can solve this in a certain number of rounds, then the distance product can be computed in a nice number of rounds. And the intuition here is that we're going to use negative triangle detection. Basically, you are going to have a you have what your current distance is between your nodes, and you want to see if that's if there's something better to do. And we're going to do a binary search over negative weights d to see if there's something better at distance d. And if there is, we'll replace that with d and keep doing a binary search. And so that's how we're using the Grover search for doing negative triangle finding, which then the distance product will feed into the all pairs shortest path. And that's really the getting the all pairs shortest path and the routing tables there is really the big speed up in terms of the number of rounds. We'll also look at, we'll need steps to do the shortest path forest and weight modifications, and construct a minimum spanning tree, and then do some pruning, but those are all fast. So really it's a step one that's important. And then, so we were able to prove this asymptotic complexity, where it's n to the fourth with some log factors. Previously, in both the classical and quantum cases, people had just hidden the log factors under the tilde notation. And when people were asking earlier what looking for quantum advantage has done to the field, I think one of the big things it's done is made us look at, quote, irrelevant factors like constants and logs, since they come into play in a big way in terms of what you can actually implement and at what point you can get advantage. And so Philip, the lead, the intern, who was an intern and is actually coming to Berkeley next year, we were all really excited about the end of the 1/4, and then I said, well, this is an asymptotic complexity. At what point does this actually, for what size does this actually give you a improvement? And we just have a few log factors to the 6th. How bad could this be over the really dumb thing of just sending all the information to one node, which you can do in n rounds? Any intuition, folks? How big does n need to be for this to cross over? I mean, my intuition was pretty bad. I thought it might be pretty bad, like, I don't know, 10 million or 100 million. Poor Philip was like, you're not going to be happy about this. So his first number was roughly 10 to the 20 nodes. And a month later, he was able to bring it down to 10 to the 18th. I said, great. If we bring it down 2 orders of magnitude every month, we'll be in great shape. And I don't know what his problem is, but no more improvements yet. So we're at, if you have any graphs of size n to the 10 to the 18 that you want to apply this to, we're in great shape. But I want to really emphasize that it's still really exciting to find asymptotic results where there's a provable difference. And often you can bring these things down, or it may inspire some other algorithms. I also want to point out that people have been looking at this in the classical case for a while, and they hadn't done the analysis either. And they're in slightly better situation. Their asymptotic results kick in around 10 to the 11, which is a little more reasonable than 10 to the 18, but still pretty out there. That's where things currently stand. But we have a lot of open questions. So big open question, of course, is can improvements be made to make this asymptotic speed up that's exciting actually be practical in some cases? And as I mentioned, we shaved off 2 orders of magnitude. What we also recognize is that if there are faster algorithms for the min-weight max matching problem in the distributed setting, that would allow for improvements in the algorithm, but we haven't been able to figure out how to do that yet. So if people have ideas on that, that would be great. That, of course, has applications to other things like decoding. Maybe a tantalizing problem for many people. Another question is other problem for which these methods can demonstrate an advantage in the quantum setting. We looked a little bit at the constrained forest problem, which is a yet more general class of problems than the survivable network design problems. But the state-of-the-art algorithm here, when you add an edge, reweights the other edges. Okay, and so that affects which edge would be added next. And so that poses a challenge for distributing in that one can't add edges to the forest simultaneously while maintaining the same guarantees. There may be a way around it, but we haven't seen it yet. There are lots of other distributed models and approaches, and very, very limited bandwidth and unlimited computation at a node, unlimited memory at a node is just one possible thing. And I think this is very interesting to look at that. I think people haven't looked that much at the distributed setting. And as further motivation, I don't know the answer to this, but there might be relations with distributing quantum algorithms in general, which is something we want to do as we scale up quantum computers, which will necessarily be networked. You'll only have a few logical qubits on a particular chip, and they'll be networked. They'll look much more like supercomputers than like your laptop or whatever. And so you'll want to be distributing quantum algorithms, figuring out what should be done and what information goes across. And I think there's lots of open work to be done here. And that's where I'm going to leave that particular thing. But I just wanted to give a couple quick pointers to some other recent work that people here might be interested in. So with Sohaib, wave, okay. We have a new family of Floquet codes. They're on a square lattice rather than a trivalent graph. Most of the previous examples were on trivalent graphs. That might mean they're more easy to implement, and it would be really cool to do a demo of a Floquet code. And this is just part of a larger program to try to understand when one can define Floquet codes, when it is useful to do so. And there are also some subtleties with respect to the distance or what errors can be corrected. So we struggled with this quite a bit, and then we just decided that's a separate paper. So we posted on the archive as we continued to think about it. And the very next day, Fu and Gottesman posted about distances in Floquet codes. We're still working through that, but they haven't given the end of the story. They've basically given an improved upper bound, but I think there's a lot more work to be done on distances in Floquet codes and what they really can correct. And then I'll just mention that we have some general protocols for efficient distillation of indistinguishable photons. So in photonic quantum information processing, the biggest error is loss. But the second biggest error is distinguishability errors of various sorts, from synchronization errors to frequency or polarization or what have you. Sort of inspired by magic state distillation, Jeff Marshall figured out a protocol a year or two ago that takes n photons that are somewhat distinguishable and outputs a smaller set of more indistinguishable photons. So those are much better inputs for quantum information processing. And we now have much more general, more efficient protocols and a lot of theory supporting that, which just came out last week. And then just because I like to, I'm optimistic about the field and like to end on a, I always like to end with Hans Mark, who I had the privilege of meeting. He brought the first massively parallel computer to NASA Ames in 1972. And sometimes I make people guess, but the peak was 50 megaflops. And that's not a typo, that's the peak. And this was amazing at that time, okay? And so when I first got to NASA and I was sitting in the supercomputer division and they're like, what is this quantum computing crap? Because they'd played with a few systems that they could access online. So a lot of the younger folks were like, you know, what is the point of this? And I'm like, don't worry, it's a physics experiment. Don't worry about it. But then some of the older folks came by and they're like, we know what you're going through. We were here in the 70s and we had to try to show the promise of parallel computing on this, what looks like incredibly limited, but at the time really amazing computer. And we're asked things like, will these processors ever be able to do anything on fluid dynamics, like compete with wind tunnels or the like? And if we in the quantum field can even have a small fraction of the impact that massively parallel computing has had on the world, I think we'll have made a big difference in life. So I'll leave it there.
Okay, maybe I can ask a silly one. Can you go back to that, maybe 3 slides back, where you had this bound between n and, yeah, here. So for that to be satisfied, I think 1 million would do. Yeah, I mean, maybe it's is the constant correct 3200? Like, if you put n equals 10 to the 6, I think that inequality would be correct.
I can't do arithmetic in my head, so we can check. But yeah, I'm reasonably confident of since we've tried hard on this. But yeah, let's check it.
It's log to the power of 6 too, but I still don't think it'll be 18. Anyways, we can check.
Yeah, let's check.
All right, let's take the rest of the discussion offline.